In the 15th century, Leonardo da Vinci, the great Italian artist and inventor, dreamed of a flying machine. He dreamed of a machine that could rise high. But he was not the first. Sergei Sikorsky.
The Chinese actually invented a string-pull toy, a miniature helicopter that you would wind up by spinning it up with a string. And this toy wandered probably along the old Chinese silk trades all the way to Europe, where it is very definitely identified in manuscripts that start about the 11th and the 12th century, and is depicted very accurately in a painting at the cathedral at Le Mans of the Virgin and Christ Child. And the Christ Child actually is holding one of those tiny little helicopter models. There's no doubt about it, in my mind, that Da Vinci himself played with such a toy, because if you extrapolate the date of the painting at Le Mans, you realize already that the toy, which had wandered by this time into France, that the painting was made when Da Vinci himself was 12 years old. So there's every possibility that he played with something similar to that.
Leonardo's helicopter drawing was hundreds of years ahead of its time, but it was theory. In 1784, the French naturalist Lannoy built a model vertical flight machine. A string attached to a wooden bow was wound around the shaft. The bow bent and became a store of energy. The string was released, and under its own power, the model rose in the air. 60 years later, Englishman Sir George Cayley designed a full-scale helicopter with separate rotors for lift and forward flight. Although his rotor designs were quite practical, Cayley realized there was no power source capable of lifting it off the ground. Through the 19th century, the steam-powered helicopter fascinated dreamers and enthusiasts. In 1878, this Italian model flew with a novel steam jet engine. Jules Verne wrote the novel Clipper of the Clouds, but vertical flight remained a fantasy. In the 20th century, some early attempts at vertical flight tried lifting mechanisms quite different from the rotor. The Grey Goose did little but frighten the onlookers. But at least the decorative window appointment showed optimism. It was the era of cut and try, of high enthusiasm and bitter failure. Some of the attempts, like the bravely named Sky Car, must have looked hopeless even to early 20th century eyes. The principle of umbrella power was never to find a place in helicopter history. But some ideas, although not successful, were closer to the mark. In 1903, the Wright brothers had demonstrated that controlled flight was possible. Even with catapult assistance, their takeoffs required a horizontal run along the ground and space to accommodate it. In September 1907, Louis Breguet's helicopter, Gyroplane No. 1, rose 2 feet in the air. It was steadied from the ground and remained aloft for 2 minutes. A month later, Paul Cornu made the first true free helicopter flight. It lasted 20 seconds. But there was an unexpected problem. Both these French helicopters were very unstable. Their piston engine still produced very little power for its weight. But by 1918, the rotary aircraft engine had enough power to lift the Austrian PKZ-2 to 160 feet and allow it to remain there tethered for up to 30 minutes. In 1921, the Russian engineer George Debotezev directed the U.S. Army's first vertical flight program. Debotezev was confident of his ability to succeed where others had failed. He built his Army helicopter in secret in Dayton, Ohio. On December 18, 1922, it made its first flight. The flight report said that it remained at an altitude of between 1 and 6 feet for 1 minute and 42 seconds. In the following year, in other flights, it lifted up to 4 people. It set a duration record of 2 minutes and 45 seconds, and in another flight, reached an altitude of 30 feet. But in spite of all this success and an improving control system, it was considered too complex and unstable for practical use. Although the Army had spent $200,000 on the project, by 1924 it was abandoned. De Beaudesat's helicopter was consigned to the scrap heap. Emil Berliner was the inventor of the Victor phonograph. He began working with helicopters in 1908. By the early 1920s, his son had joined him, and in 1922 they produced their most successful model. It had two separate rotors mounted on wings, with the engine in the nose. The engine drove the rotors so they rotated in opposite directions and canceled out each other's torque. There was a third propeller at the rear of the fuselage to increase or decrease lift. But too many problems arose. The rotors were too small, and the aircraft was unstable. The Berliners withdrew from the helicopter race. Etienne Omichen was a French auto engineer who worked for the Peugeot company. In the 1920s, he made several unsuccessful attempts to build and fly large twin-rotor helicopters. Eventually, he fitted a gas-filled balloon to help the helicopter off the ground. It was a compromise, but Omichen was persistent. By May 1924, he had abandoned the balloon and built a new helicopter. It established a world first by flying a 1-kilometer triangle course. But while his days of wrestling with balloon-assisted helicopters were over, even his new design was highly impractical. The Argentinian-born Marquis Pescara was Omichen's competitor in setting records. His helicopter was highly innovative. It had two coaxial rotors, each with a double-connected set of blades. The Pescara helicopter was capable of some degree of cyclic pitch control, and Pescara is recognized as a pioneer of control systems. His helicopter was the first to be capable of safe landing under auto-rotation in the event of engine failure. Pescara achieved a speed record of 8 miles an hour for almost half a mile, and his helicopter once reached an altitude of 30 feet. But the Pescara helicopter was still not practical enough for sustained flight. In the early 1930s, Belgian Nicolas Florijn came up with a radical change in helicopter design. It was a tandem system, with rotors mounted on the front and rear. It flew for the first time in April 1933. In one flight, it reached an altitude of 20 feet and stayed there for 8 minutes. The rotors revolved in the same direction, and they had to be tilted on their axis to counteract torque. But Louis Breguet, whose helicopter rose 2 feet in 1907, was back in rotorcraft design. In 1935, he produced the gyroplane. It had coaxial rotors, and the blades were articulated for stability and control. It was the first helicopter to perform convincingly in free flight. This is not a helicopter. It's an autogyro. The propeller drives it forward, and the unpowered rotor acts like a wing. Spanish designer Juan de la Cierva had pioneered the autogyro in the early 1920s. His genius was to realize that an unpowered rotor would revolve in flight because of pressure of air on the underside. The autogyro was not a helicopter. It was an airplane capable of flying with rotary wings. In 1928, Cierva made the first autogyro flight across the English Channel. He'd already made his home in England, setting up the Cierva Autogyro Company in 1926. The company could not keep pace with demand, and Cierva was forced to license his design for others to build. Cierva developed the autogyro because of his interest in aircraft safety. Autogyros could take off quickly in a small space. They could also land with very little forward speed and a very short run, so they didn't need a runway. They would never stall, and if the engine failed, they would simply glide to Earth in auto-rotation under complete pilot control. In the 1930s, there was an international boom in the popularity of the autogyro. It was seen as the car of the sky, and Sierva traveled widely, demonstrating its capabilities and accepting international acclaim. One of the major centers of interest in the autogyro was the United States of America. It was promoted there by fixed-wing aviator Harold Pitcairn, designer of a famous line of mailplanes. Pitcairn had bought a license from Sierva to manufacture autogyros in America. His main object was to use the basic safety of the autogyro to reduce accidents in the air. It was ironic that Juan de la Sierva would be killed not in an autogyro accident, but in the crash of a fixed-wing commercial airliner. In America, Harold Pitcairn set about building his own line of autogyros. His second model, the PCA-2, had short wings, which allowed it to use a control system generally similar to fixed-wing airplanes. It had ailerons for banking, elevators for dive and climb, and a rudder for directional control. The rotor was flexible, with hinges at the head. In forward flight, a simple rotor is unbalanced because more lift comes from the advancing side than the retreating side. Juan de la Sierva had developed hinges that allowed the rotors on the advancing side to rise without tilting the body of the aircraft. The PCA-2 had a system that brought the rotor up to speed without the need for long taxiing. The rotor was connected to the engine for startup and disengaged as the takeoff roll began. This system allowed the PCA-2 to make short, steep takeoffs. In the air, it could reach speeds up to 120 miles an hour. But if it had a headwind, it could match the speed of the wind and hover over a fixed point on the ground. The PCA-2 was very maneuverable and was capable of slow flight with a high degree of control. The idea here was that a line could be trailed at running speed and a person on the ground could attach or retrieve a payload. But it wasn't all business. The PCA-2 was capable of surprising tricks. The autogyro proved to be an effective crop duster. It could fly slowly to give a thorough covering, and the draft from the rotors distributed the spray more thoroughly than a fixed-wing aircraft. The famous aviatrix Amelia Earhart had a special relationship with the Pitcairn autogyro. She set an altitude record of 18,415 feet in the PCA-2 and also flew it coast to coast. Although more and more a part of the American skyline, an autogyro straying into a no-parking zone was still likely to turn heads. But public officials could be influenced by the offer of a joyride. In the early 1930s, autogyros became a familiar sight over the cities of America. They were promoted as the answer to urban traffic jams and were used for jobs like advertising and journalism. Right from the start, Pitcairn was unable to keep pace with the demand. He'd produced 58 autogyros before he sublicensed his franchise to Roderick and Wallace Kellett. The Kellett Company was to become a major rotorcraft producer over the next 20 years. The Pitcairn PA-22 had no wings. It used Sierva's principle of controlling the direction of flight by tilting the rotor. A small rudder helped maintain stability at low speeds. The PA-22 could make a jump takeoff, and in 1935, it flew the first mail run from the roof of the New Philadelphia Post Office to Camden Airport across the Delaware River. The Pitcairn AC-35 was special. It had something new to show the nation's capital. In the air, the AC-35 behaved just like any other autogyro, but on the ground, it could transfer engine power to the tail wheel. It could be steered through the front wheels and driven around like a car. When war in Europe broke out, Pitcairn demonstrated the PA-22 to the military. American helicopters were still not practical, and the Army was interested in the PA-22's ability to land in places inaccessible to other aircraft. The demonstration was impressive enough to convince the Army to buy the larger PA-33, which was capable of speeds up to 150 miles an hour. The growing threat of war caused the Army to look closely at a range of different Pitcairn autogyros. The PA-36 could jump takeoff with no forward run. On the ground, the rotors were set at zero pitch and spun hard by the engine. When the pilot suddenly released the rotors, they bit into the air and it leapt straight up. The pusher autogyro had potential for observation work, and 7 production models, designated XO-61, were ordered by the Army. The PA-39 was built for British use and had the unique ability to land and take off on ships at sea, 3 years before this was possible with the American helicopter. This gave it potential as a weapon to protect transatlantic convoys from German U-boats. German sea power was a problem for the British, but German air power had a real technological edge over the rest of the world. In August 1939, the gas turbine-powered Heinkel HE-178 had flown. Fortunately for the Allied forces, the German Luftwaffe failed to capitalize on its lead in jet-powered fixed-wing aircraft. But the Germans had another technological edge, one they had established as early as 1936. They had a practical, flyable rotorcraft. Not an autogyro, but a true helicopter. The Foch-Achilles FW-61. The FW-61 made repeated sustained flights, and in 1937 had stayed in the air for over an hour. It could lift vertically off the ground, had reached altitudes of 8,000 feet, and could fly at 77 miles an hour. One of the test pilots was the famous Hanna Reich. In 1938, she began a series of demonstration flights to the German public. In February, she made the world's first indoor helicopter flight in the Deutschlandhalle in Berlin. This demonstration was repeated daily over the next 2 weeks inside the 100 by 300-foot auditorium. The FW-61 was built from the fuselage of an FW-44 biplane trainer. It had no wings and was lifted by 2 rotors raised high on outriggers. Counter-rotation canceled the effect of torque from the BMW radial engine. The Foch-Achilles FW-61 was a milestone in vertical flight, and it gave the Germans leadership in the helicopter field. The flimsy little Foch-Achilles FA-330 was not a powered helicopter. It was an automotive kite, designed to be towed by a submarine and used for reconnaissance. It needed a forward speed of 17 miles an hour to become airborne. This is a test flight, but 200 were built and introduced to active service on U-boats. The first German helicopter to go into production was the Flettner 282. It made its first flight in 1940, and the German Navy eventually ordered a production run of 1,000. But only 22 prototypes were completed. In 1942, it became the world's first helicopter in operational military service. It was designed for a variety of tasks in the German Navy, including liaison and communication. One is said to have landed on a moving submarine. Flettner pioneered the system in which two side-by-side rotors were geared to intermesh and rotate in opposite directions. It was stable and reliable, once flying for 95 hours with no repairs or replacements. In America in 1940, the most promising rotorcraft was still the autogyro, with its ability to perform a jump takeoff. But soon that would change. Igor Sikorsky, a white Russian refugee who came to America in 1919, would change forever the shape of the helicopter.
In the 1950s, the world became familiar with the military helicopter as a machine of mercy, an airborne ambulance that would whisk injured men from Korean battle zones to hospitals. A decade later, American fighting men returned to Asia, this time facing a much different type of war. Vietnam was a guerrilla war. The enemy would strike and then disappear. There was little doubt that the Army needed a faster mode of transportation to keep up with the enemy. Enter the Bell HU-1 Iroquois, fondly known as the Huey. This was no airborne ambulance, this was a fighting machine. Those that weren't used as troop transports were modified with 30-inch machine guns and rockets to escort the unarmed troop ships in and out of battle. The development of these helicopter gunships changed the nature of close air support. Helicopters were highly maneuverable, speedy, and could get down and dirty with the ground troops in a way that jets could not. The first Army Huey was the root of the American combat helicopter family tree. While one branch spawned an entire family of helos built specifically for transporting troops and supplies, another branch gave birth to the Cobra, the first pure attack helicopter. A worthy successor to its early gunship ancestors, the Cobra nonetheless had its Achilles heel.
With the Cobra, it had its primary anti-armor weapon was the tow missile, and it only had a range of 3,750 meters. That means in order to shoot a tank, you're getting close to being inside the tank's main gun round range.
The Army began looking ahead to the next generation of attack helicopters, and by 1975, they had two candidates. Bell Helicopters, the creator of the Huey Cobra, pitted its prototype AH-63 against the AH-64, made by rival manufacturer Hughes. After 850 hours of rigorous flight and ground trials, the Hughes AH-64 Apache emerged as the winner. 7 years of modification followed, including the acquisition of Hughes helicopter by aviation giant McDonnell Douglas. The first Apaches were delivered to the Army in early 1984. The Apache was easily the most formidable attack helicopter the world had ever seen. Imbued with all of the elusive, aggressive traits of its namesake tribe, the Apache was built to provide fire support to units in the field and to take out high-priority targets. More specifically, it was built to kill tanks. The Apache is a menacing aircraft, even stripped of its weaponry. In flight, it looks like the world's deadliest dragonfly. Its rugged exterior mirrors its durability.
Everything in this aircraft's designed to crash. If you were to get shot down or something like that, it's designed to if it crashes, it's designed for the crew to live. The 30 millimeter, it will jam up in between the front seat and the back seat. There's an actual space there for it to crush up into. The struts are designed to take a heck of a hard landing, and they're designed to crush all the way up, so the wheels would be up level with the pilot's head.
Armor made of boron carbide bonded to Kevlar shields the Apache crew and the helicopter's vital system. The protective layers surrounding the airframe and the crew seats can withstand the most small and medium anti-aircraft artillery. The blast shield between the two crew members guarantees that no single round will kill both pilots. Even the gas tanks on the Apache have their own defensive capability.
Basically what happens if a projectile goes through the fuel tank there, there's a gel in there. When it mixes with JP fuel, forms like a big glue, if you want to call it glue, and it'll seal the hole. It'll basically seal the hole.
The muscle of the machine, twin General Electric engines, is shoulder-mounted on the fuselage behind the main rotor mast. The engines are physically separated and run independently, so if one takes a hit, the other can keep the Apache flying. The Apache's main rotor has 4 blades made up of stainless steel spars and glass fiber tubes. The blades can slice through tree branches up to 2 inches in diameter and can survive 50 caliber machine gun rounds and shell strike. With a top speed of close to 200 miles an hour, some pilots liken flying an Apache to driving an expensive sports car. Its controls are incredibly responsive to a pilot's every command. But speed, durability, and maneuverability alone are not enough. An Apache without firepower is like a gun without a bullet. The Army designed the Apache as a platform for a new generation of weapons. One is the laser-guided Hellfire air-to-ground missile. The Hellfire can pierce the armor of any known battle tank from more than 3.5 miles away.
What it does basically is we designate targets on a battlefield with our laser, with a coded laser. The missile, before it leaves the rail, knows our laser code. When we squeeze the missile off, it finds a laser beam, it rides, so to speak, that laser beam to the target.
Hellfires are ounce for ounce more expensive than gold. The Apache can carry up to 16 Hellfires on its outboard rails, though a load of 8 is more typical. The accuracy and effectiveness of the weapon is unquestionable. The Hellfire is the premier anti-tank missile in the Army's inventory. It's what the military calls a standoff weapon. It inflicts maximum damage from a maximum distance. But when you're close enough to the enemy for a bare-knuckle brawl, hanging tight below the cockpit, the chain gun packs 1,200 rounds of 30mm punch. Two stud wings on either side of the Apache carry Hydra rockets. The 2.75-inch folding fin rockets can be armed with a wide variety of warheads.
We can use multiple purpose submunitions, which each rocket will carry 9 submunitions, and they burst in the air and they fall down and they'll cover a large area with small explosions. It's kind of a poor man's cluster bomb.
The Apache can launch its 38 rockets in a variety of combinations or all at once. That's a feeling pilots can only describe as a real rush.
Not only do you feel it, you smell it. You smell the forward as the 38 rockets leave the aircraft and the smoke that it leaves behind.
Strapping into an Apache is like climbing down into an Indy car. Not an inch of space is wasted in its sleek interior. The two crew members sit in tandem, with the pilot occupying the rear seat. His perch is more than a foot higher than the gunner's, providing a clear field of vision. While tasks are divided between the crew members, both are fully qualified pilots and both know how to operate the aircraft's weapons system. Stowed under the gunner's seat is the full set of flight control. But unless there's an emergency, he's focused on acquiring and destroying target. Not long ago, helicopter crews were virtually grounded once the sun went down. The surest way to wrap your helo around a tree was to fly at night. But for Apache pilots, nightfall is when the fun begins. As they slip on their high-tech helmets, another world emerges, a world where night becomes day.
Well, it was designed to fight and fly at night with an infrared system, and the pilots fly off a HTU. It's a little reticle that comes down over your eye. You can fight, fire, fly, all through that little TV screen.
There's a lot of information jammed into that little television screen. The pilot sees an infrared image that allows low-level map of the Earth flight, along with symbols that tell him how high and how fast he's flying. Maneuvering with one eye takes some practice. It's a skill pilots say that if you don't use, you lose. The helmet is connected by wires to the aircraft's weapons control system. Either crew member has the option of slaving the 30mm cannon to his helmet, so the gun automatically points wherever he looks.
It basically does a little trigonometry. It knows how high the helicopter is, what the look-down angle of your head is, and it does a little trigonometry and it figures out the range. If we were in a battle position, and the front seater is engaging targets, looking a long ways away, the back seater is worried about what's happening around him. So the back seater could have control of the gun, slave to his helmet. He could be looking to see if there's any bad guys around him, and just suppression and keep them away while we're concentrating on what's going on downrange.
Because the Apache is a sexy, state-of-the-art machine, competition to fly it is fierce. Only the strong of mind, body, and spirit need apply. Potential pilots go through 9 months of basic flight school, and only then can request Apache duty. They undergo an additional 3 months of intense training. They log countless hours of flight time in simulators. The simulators are virtual reality that is virtually real. Pilots respond to one computer crisis after another to test their performance under pressure. While nothing can take the place of actual flight, the time spent here pays big dividends when the student straps on his first Apache. Once they graduate from flight school, pilots report to their operational units, but their schooling is never really finished. Skills need to be constantly fine-tuned, so the Apache pilot is totally prepared for the inevitable battle that lies ahead. The Apache received its trial by fire in December of 1989, during Operation Just Cause, the American invasion of Panama. A handful of Apaches, flying mostly at night, helped oust Panamanian strongman General Manuel Noriega from power. But the world would wait several more years before it heard the full battle cry of the Apache.
The liberation of Kuwait has begun.
Sam, got him. Shoot in a 6-1. Get your target. Heading 160. Sam.
The coming weeks provided the Apaches a wealth of targets. They skimmed the desert floor at incredible speeds, night vision guiding them through the dark maze of battle to destroy skewers of Iraqi targets. Smoldering cinders of enemy bunkers and trucks provided grim proof of the lethality of the gunship's rockets and cannon fire. But most Apache pilots prefer the anonymity that comes with distance, a luxury that the Hellfire provides.
Is we'll have to pop up, find the target, get a range to it, come back down. Shoot the missile will fly a pre-programmed trajectory over the hill, and we'll have a time of flight countdown. And as long as we pop up and we squeeze laser on the target for the last 8 seconds of flight, we'll be able to kill it.
Countless Iraqi tanks met their end without a clue of what hit them or where it came from. Though the Apache was successful in the open desert, the ideal battlefield for these pilots would provide a few more places to hide.
I was out in Saudi, you have nothing to hide behind. You feel like you're naked, basically. What we have is our standoff. With the Hellfire, we can stand off approximately 8 kilometers from the enemy. But that in itself, at times, if weather conditions are bad enough where you have to scoot in closer to the enemy, you tend to feel naked because you have nothing to hide behind. I would prefer to have hills, vegetation that I could put this aircraft behind and pop up, scan the battlefield, and I can videotape the battlefield, return to my mast, my safety, review my tape, and then prioritize my targets at that point, and then launch my Hellfire.
The future of the Apache has arrived in a variant called the longbow. The longbow looks just like a regular Apache, except for a knob on top of the main propeller mass. That knob contains millimeter wave radar, which enables the gunner to guide up to 16 missiles at a time. The radar is mounted high, allowing the helicopter to stay hidden while scanning the battlefield.
With the longbow and the radar fire control, as long as the radar is exposed, it can find the targets and classify the targets and prioritize the targets, all without having to be exposed to the enemy. And they can shoot their radar-guided missiles, and they can get all the missiles going to a different target at one time.
As this new branch on the helicopter family tree continues to grow, no one knows which direction it will stretch. The only certainty is this: no enemy tank in the world today can ever feel safe with the Apaches on the prowl.
Amphibious assault. That's the environment for the Cobra gunship of the Marine Corps, the AH-1J and the AH-1T. The Cobras have a variety of missions throughout the amphibious operation, escorting the transport helicopters during the ship-to-shore movement, supporting their landings with suppressive fire, escorting and scouting for marine armor ashore, helping to control supporting arms, marking targets, and attacking enemy armor with a multitude of weapons. The AH-1J and T are virtually identical, except that the T is a tow cobra, able to fire the tow missile. There are also minor differences in maneuvering ability. Cobras operate in two plane sections wherever possible, for greater firepower and mutual protection. Maneuverability, agility, and small size make them difficult targets for enemy fire. This is an all-weather helicopter with IFR flight capability. It can operate at high altitudes if necessary, up to 10,000 feet. It's fast for a helicopter. Maximum speed in a dive with full ordnance load is 170 knots. The Cobra's prime operating area, however, is close to the deck where it's onto an enemy and past before he knows it's there. Cruise speed is 140 knots, with a mission radius of 100 nautical miles. Visibility is unobstructed from the front seat, where the co-pilot usually rides. Both pilot and co-pilot are protected by armor plates and wear bulletproof vests. All Cobras carry 3-barrel 20mm Gatling guns with 750-round magazines. Rate of fire is 650 to 750 rounds per minute. This unusual weapon can be locked for the pilot to fire dead ahead, like a fighter plane. Or it can be trained, depressed, and elevated, fired from a remotely controlled turret by the co-pilot, using a telescopic sight unit. The gun can be trained to 110 degrees either side of center. The wide angles of fire, plus excellent crew visibility, giving the Cobra fast response to threats from any direction. It can be depressed 50 degrees and elevated 15 degrees. Along with the 20mm Gatling gun, there is a choice of other ordnance. The Cobra can carry up to 52 high-explosive and white phosphorus rockets in 4 pods, with 1 7-shot pod and 1 for 19 rockets on each side. The tow Cobra can substitute 4 tow missiles for one of the rocket pods on each side, carrying 8 tows in all. Other combinations are possible, depending on the demands of the mission. Here is some of the available ordnance. Gun pods, with additional Gatling guns firing forward only. Dual air explosives, and flare canisters, each with 8 flares, fired in pairs. The Cobra carries a lot of firepower, but if it's loaded with everything it can hold, fuel quantity has to be reduced. Normal procedure is to carry enough fuel for the mission, plus an ordnance configuration tailored to the job at hand. The Cobra's versatility makes it an integral part of the amphibious assault, another weapon in the Marine arsenal. It becomes the eyes of the armored columns. It escorts and defends troop-carrying helicopters. It serves as a spotter for naval gunfire and artillery. It can mark targets for attack aircraft and control all types of close air support. Like all these systems, the Cobra exists to work with the ground troops. It is a tool of the landing force commander, assigned to the support of his units at any level, equipped for constant communication with command posts below, so that it can respond to changing needs as the situation develops. The Cobra's first mission in the amphibious assault is usually escort of helicopters carrying assault troops. At least 2 Cobras are normally used, deployed according to the expected threat and the terrain. In this case, the enemy threat is frontal, so the gunships lead the flight. The Cobras may fly behind if the threat is from the rear, as it often is on returning from the landing zone to the ships. If the enemy is believed to be a threat from all sides, the escorts may change their deployment constantly throughout the flight, but always in planned patterns. Station keeping and attention to schedules are vital during the ship-to-shore movement. The naval gunfire and supporting aircraft may be walking the flight in, laying down fires just ahead. Terrain is used wherever possible to mask the movement of the flight. The Cobras shift position as required by the terrain and by expected opposition. The escorts must be ready to drive off enemy helicopters, but must not leave the flight to pursue an enemy. The Cobras return any fire which could be a danger to the flight, but only long enough to distract the enemy from the transport. While the Cobras engage the enemy, the transports have a chance to get by without damage. At the landing zone, the lead Cobra pulls away from the flight and makes passes over the LZ to see if it's hot. The Cobra may fire 20mm shells or drop fuel air explosives to detonate booby traps and flush out defenders. As the transports approach, the gunships move to their second major task, support of the helicopter landings, with landing zone suppression fire. The troops and the transports are most vulnerable during offloading. The Cobras go into a protective pattern above the LZ, usually a butterfly, firing at any targets which could threaten the landing. The attack helicopters may break their pattern to respond to calls from the ground commander for strikes against specific targets around the LZ. The Cobra's job here is protection of the landing. They fly their protective patterns as long as the transports are on the ground, then normally escort them back to the beach unless the ground troops are in trouble and need their support. The return flight always takes a different route. If the area below is hot, supporting fires may walk the flight back to friendly territory. Again, the Cobras shift deployment as needed to guard against the most likely threat. The escort mission usually ends at the beach. Now, let's look at other Cobra missions as the amphibious assault proceeds. The Cobras pick up a Marine armored column. Escort and scouting for service convoys is another of their jobs. The attack helicopters have standard escort patterns for ground units, just as they do for transport helicopters. If the surface unit comes under enemy attack, Cobras respond with suppressive fire to allow the ground unit to get by, or to cover it as it turns back. The ground commander may ask the gunship to scout ahead of the convoy, conducting reconnaissance by observation or by fire. The Cobras often shoot into suspected defensive positions to draw fire and reveal the enemy. If an enemy position is discovered blocking a route of advance, the ground commander may ask the Cobras to search for an alternate, less well-defended attack route. The task here is to help the ground commander conduct his attack effectively. The Cobras become the eyes and ears of the armored column, expanding its field of view. The Cobra pilot can drop in on a ground commander to discuss a complex situation. This is called a Zippo brief. The ground commander has a set form for the brief. He is able to give the pilots only the information they need for the mission in organized fashion. In this case, the Cobra is to mark a target for jet attack. High-performance jets are unable to slow down to consult maps and pick out targets. A Cobra can sneak out of concealment nearby and mark the target with white phosphorus. Or he can stand off 4,000 meters and lob his Willie Feet rocket onto the target. And stay there to control the mission, advising the jet pilot by radio that the marker is on target for a specified distance off. The Cobra can coordinate supporting fires, popping up from concealment to observe a situation. Most Cobra pilots have completed schools for both artillery and naval gunfire coordination, and can also serve as forward air controllers. In addition to radio contact, Cobra pilots can land at artillery positions for first-hand planning or for passing on of missions. Even though this Cobra is coordinating supporting arms, it carries a variety of ordnance to be ready for any mission assigned. When a Cobra pops up from concealment, it may be for more than observation or control of supporting arms. It may be for direct attack on enemy armor. The tow Cobra can be a deadly killer. Two Cobras lie in wait. Their primary targets are anti-aircraft vehicles and tanks, then armored personnel carriers. One Cobra pops up. The other remains hidden. The lead Cobra pinpoints the target location after a quick look, and the co-pilot passes the information to his teammates. The second aircraft then pops up at a different location, and it fires. After firing, both Cobras take evasive action and move on to the next attack position. An attack on enemy armor may also involve two other Cobras further from the target to divert the enemy's attention and furnish protection for the attacking Cobras. An attack is often coordinated with diversionary raids by other supporting arms as well. Cobras begin to engage with tow when enemy armor gets within 3,000 meters or so of the FIBA, while the enemy is still occupied with other attacking elements. Stop him. Turn him around, or at the very least drive his troops out of the armored carriers and into the open, where they are slow and vulnerable. That's the object of a tow attack on enemy armor. Those are the tasks of the Cobra in an amphibious operation. Success depends on the aircraft's ability to operate from many types of amphibious ships, and on those ships maintaining a supply of parts and ordnance to support the Cobra missions. Many tasks depend on the Cobra's ability to operate after dark and in reduced visibility, with all aircraft IFR equipped and their pilots fully qualified. Cobra squadrons are ready for immediate deployment at any time, with aircraft, spare parts, ordnance, and all gear ready and marked for embarkation. Cobra squadrons spend about a third of their time aboard ships or at bases away from home. The squadron is in constant training to upgrade proficiency and combat readiness for both people and equipment. It's a long road to combat qualification for a Cobra pilot. It has to be to prepare him for the variety of tasks given to a Cobra squadron. The normal road runs directly from college to officer candidate school for 10 weeks. Then to basic school for 6 months or so of air and ground tactics. And on to flight school for a year to 18 months, first in fixed-wing aircraft and then in helicopters. When he gets his wings, he has about 200 hours of flight time, and he's been in school and training for at least 2 years, without counting college time. When the new pilot reports to his squadron, he's usually looking at still another year of training to be combat qualified. On escort duty, scouting for an armored column, working with high-performance jets, attacking enemy armor on its own, the Cobra has carved its own niche in the arsenal for amphibious assault. Today, it is an almost indispensable weapon to the Marine Corps.
The title of this film may be a little misleading, because to most of you, the AH-1S turret and rocket management doesn't represent the introduction of a new system. Rather, it is a system refinement based on Cobra weapons with which you're already partially familiar. The Chin turret system is a case in point. It has an M197 20mm gun with a capability rate of fire limited to 750 shots per minute on the AH-1S Series 50 ammunition. The turret is electrically driven in azimuth and in elevation. Direct drive DC motors through a gear train supply mechanical power for driving the turret. The servo amplifiers are in the Universal Turret Control Assembly, located on the right side of the aircraft at the gunner station. Positioning of the weapon is by means of the familiar helmet sight. It makes gun control virtually instinctive. By selection where the pilot or gunner looks, there the gun will point automatically. The gun moves left or right in azimuth 110 degrees, a total of 220 degrees. The normal slew rate is more than 80 degrees a second. In elevation, it varies from 11 degrees to 21 degrees up and 50 degrees down. With such rapid turret traverse, be sure when the gun turret is energized that the area is secured. This will prevent someone being accidentally struck by the gun should the turret be rotated. If there is a loss of any electrical power or master arm is turned off, the turret will go to emergency stow position 11 degrees up and 0 degrees azimuth. During ground maintenance operation of turret, the emergency stow circuit breaker should be pulled to prevent the emergency stow from activating. Here's the gun feed system. It is a proven design, classic in its simplicity. Note the similarities between the 7.62 gun feed system on the original AH-1G more than a dozen years ago and the 20mm feed system on your new AH-1S. Conceptually, they are similar systems, but there are many refinements. Here's a small but important example. By activating the loading switch, this electric motor pulls the linked 20mm rounds from the box and pushes them into the section of flexible chute that connects to the gun feeder. This booster motor eliminates the excessive belt pull loads that would be found if the delinking feeder were the only source of power. The booster motor also eliminates the need to manually fill the chute during loading operations. Although this turret is a growth version of the proven M28 turret, the 20mm M197 weapon provides vastly improved combat punch when compared to the 7.62 round. This is test footage of the gun system taken during its qualification at Yuma. But this gun system has been through more than just an extensive Army test program. It is the same weapon which has been in operational use with the Marines on their AH-1Js. So it's a proven system, one which should enter the Army inventory with minimum growth pains. Recoil is obviously a problem with any 20mm cannon. You'll notice this single recoil adapter located above the gun drive assembly. There's also a compensation circuit running to the aircraft's SCAS system. This means that appropriate aircraft attitude changes are made through the SCAS whenever the gun is fired. Which leads us to another electronic compensation. It's the way the gun takes its own Kentucky windage, the automatic corrections for aircraft speed and gun attitude. These small sighting corrections are automatically fed to the gun as a target is being tracked throughout the 220-degree field of fire. Turret system test and checkout is a simple routine operation. This single test set will check out the entire system. W1 connects to the aircraft power source. W6 is a multiple lead cable that connects to the gun control assembly through the fairing access door and to the logic control unit and test connector 19J1. Now you're ready for an operational check of the turret system. Use of the test set is detailed in TM-9-1090-206-12, but we'll just briefly look at some of the functions. There are several important safety considerations before starting a system checkout. All wing stores should be downloaded. W3J1 should be disconnected from W2P1. The gun, feeder, and feed system should be clear of ammunition. In short, no ordnance should be on the aircraft. These are all common sense procedures, but they must be done in sequence, so just follow your TM checklist, and you'll soon be ready to begin the operational check of all turret systems. You'll find operation of the test set straightforward. There are 16 keys for test selection and command functions, plus reticle, pass, and fail indicators. There are 9 separate functional checks, the first being power distribution and test set connection, followed by a test for fixed forward servo stability. There is a check to verify the gunner's turret stow position. There are 3 TSU tests: tracking, turret depression limits, and a tracking out of coincidence check. Slow turret slew and forcing function are covered in the next test. And the last 2 tests verify gun trigger application and release. When a fail condition exists, there are fault code numbers displayed on the test set. These numbers and the fault code table in the TM will help to diagnose the malfunction in the system. This has been a quick overview of the M197 Universal Turret. You may well ask why call it universal when all we've shown is the 20mm M197 gun. Well, it does accept other weapons. The M134, for example, the proven Cobra minigun, 7.62mm. And perhaps most important of all, Growth capability is designed into the turret, so if future tactical needs dictate even larger caliber than 20 mm, the system is designed to accept the M230E1 30 mm chain gun. Now let's take a look at the rocket management system. Wing stores have been important since the first attack helicopter, and although the stores might not look too different than other Cobra versions, there is a significant difference in capability. This control and display unit is the heart of rocket management. It permits the pilot to select the precise rockets needed for specific mission requirements. We'll use animation to show the relationship between the zones of the display unit and the specific rocket tubes which they control. Zone 1 is the outer ring of rocket tubes on the outboard launchers, a total of 24. Zone 2 contains the top and bottom pair on the inner rings of tubes, again, the outboard launchers. This is a total of 8. Zone 3 is similar to Zone 1, the outer ring of tubes, only this time on the inboard launchers, again a total of 24 tubes. Zone 4 is similar to Zone 2, only inboard launchers again, a total of 8 tubes. Zone 5 is the 3 center tubes of all 4 launchers, a total of 12. Now you'll notice that the 5 zones have thumb wheel counters which can be set to indicate the type of rockets which are loaded in the specific zones by aircraft armament personnel. And just above each zone arm switch is a rounds remaining counter. The LED readout will decrease each time any rockets are fired, so the pilot knows exactly how many rockets and what type he has available. The zone arm switches are located below these rounds remaining readouts. These switches are pictorial and have a symbolic representation of the specific zone of rockets which they control. The first thumb wheel at the bottom of the panel selects rocket penetration in meters, thus enabling the explosion to occur a predetermined distance after foliage canopy penetration. The increments are in 5-meter intervals from 10 to 45 meters. There's also a super quick setting for point detonation. An additional bunker setting will detonate the rocket after penetration of dirt and logs up to 3 meters in thickness. Rate selects 3 rates of fire: automatic, slow, and fast. In general, the automatic setting will be used since that is the optimum firing rate for the specific type of rockets being used. Mode is a selection of firing. Quad, 1 rocket from each of the 4 launchers. Pairs, 2 rounds, 1 from each side of the aircraft. And single, 1 round, alternating from each side of the aircraft. Quantity is a multiple of the mode switch. It varies from 1, 2, 4, 8, and all. So if the pilot selects 8 for the quantity and has the mode of quad, the system will sequentially fire 32 of the selected rockets. The range switch activates the computer which sets the M439 fuses. The range is adjustable from 500 to 6,000 meters in 100-meter increments. The range switch has an A automatic position for future use with a fire control computer. Until the FCC is incorporated, the A position sets the M439 fuses for 3,000 meters. The press to test switch can be used either in flight or on the ground. The master arm switch on the armament panel must be in the standby mode in order for the test sequence to be initiated. The test validates the entire subsystem, including all associated aircraft wiring. We have spent quite a bit of time going over the cockpit display unit because understanding what it does and how it manages the rocket system is very important to armament personnel. Obviously, the loader must load specific rockets in their respective zones in order for the system to work correctly. Within each zone, the loading can be random, but different rocket types for each zone must be kept separated. Bear in mind that there may well be times when only partial rocket loads can be used. Warhead, weight, altitude, high ambient air temperature, and full fuel loads are factors which can combine to limit the payload that the S can carry for certain stringent missions. Using the bit features of the subsystem, a maintenance technician is able to detect, locate, and correct problems which may occur within the armament loads. Here, a round was not seated properly within the launcher. Or this tube has a rocket which has not had the hook connected. Even defective rocket motor squib can be detected with this bit equipment. Replacement of individual LRUs is easy. Each LRU has a mechanical fault indicator. The flag is tripped anytime a malfunction occurs, so replacement can quickly be made. One of the more sophisticated aspects of the rocket management system is the RC fuse subsystem. This is a completely automatic computer system which sets the fusing of each rocket on an individual basis. It automatically compensates for the up to 20% fuse tolerances and gives each rocket an individual fuse setting to achieve the specific range which has been selected. It's the most sophisticated part of the fire control system, but it requires no maintenance other than replacement of any defective LRU. Repairs of these faulty LRUs present no real problem at the intermediate level of maintenance. A single test set is sufficient to isolate the fault, make a diagnosis, and enable you to make repairs. The whole rocket management system has been designed for high reliability and maintainability. No introduction would be complete without a mention of some of the airframe changes that are found in the AH-1S. Perhaps the most important is this new 10 kVA alternator. It makes available through a rectifier 200 additional amps of DC power. That means that this new alternator or the start generator can operate the turret. Such redundancy provides a high degree of combat survivability and increases the probability of mission success if one system is damaged. This has just been an armament preview of the newest version of the Cobra, the AH-1S. Coupled with an already existing tow missile capability, it means that your aircraft can now bring an even greater variety of more potent firepower against a wider variety of targets. All Army aviation technicians perform valuable work, but when it comes to the 68M and J MOS, the work is perhaps even more important, because nobody contributes more to the direct success of the aircraft in its specific combat mission than the work of you armament technicians. Another man's finger may be on the trigger, but in a very real sense, the weapons are in your hands.
5 lines, 6 lines, 6 lines, 5 lines.
Yeah, he doesn't say left 200. Left 200 over.
Where's the binos?
He doesn't normally got NCOs on.
No.
Thanks.
Hey, the binos are in the day pack.
I noticed that when we were doing the fucking.
There is?
Back up.
See, up 40 and fucking.
Dodge 8756, extension of Venom 11's window to time 18. Status of reattacks. Venom flight reattacks complete. Push and call. Hey, F6 147. We're done by get you immediate assist rate. Roger. Immediate suppression on that grid.
Max Sword 7,000.
Max Sword 7,000.
That's reporting 7 o'clock. I'd also like to work. Good impacts. Watch 6-4 from lead.
that effect.
Fuck yeah.
Picture putting together a massive jigsaw puzzle where most of the key pieces are missing. That may give you some idea of what the past year has been like for Master Sergeant Cliff Long. As soon as he donated AH-1 Cobra arrived, the mechanic knew restoring it would be a challenge.
And it basically arrived in about 5 different boxes. And we're talking about multi-packs, huge 4x4 boxes.
Even with all those parts, Long fell well short of what he needed to make the Cobra complete enough to be part of a static display at the Combat Readiness Training Center in Gulfport. The 1108th Aviation Group reached out for help across the Department of Defense.
The Cobras have been out of the system since about 1996. This aircraft came mostly stripped down, and every part on it was donated by other DoD agencies and the word of mouth.
The 1108 didn't hesitate to go the extra mile by installing some components that won't be visible to the public, like a working transmission. That's from the Guardsman's desire to recreate memories as authentically as they can.
We're going to go back to a basic paint scheme that the Army paints, which is green. We're going to put all the markings, the original markings back, some sharp teeth on the front, because this is an attack helicopter.
Those that served in Vietnam, it's something that they'll see on the side of the road and they have to just stop. They have to walk over there and they have to look at it and they have to tell the loved ones or whoever they're with that this airframe saved my life.
Soldiers say this restoration is dedicated to those veterans who lost their lives in the name of freedom. For the Gulfport CRTC, I'm Danielle Thomas.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.